Today we're learning how to graph exponential functions. Graphing exponential functions uses transformation rules that we've been doing quite a bit this year, so shifting left, right, up, down, stretching, shrinking, and reflecting across the x-axis. Okay, so right at the top of the page, you guys have this box where it just has some basic info about exponents. Of course, there's multiple rules about exponents, the product property, the power property, the quotient property, and so on. But if you just remember a couple of basic rules, you can figure them out without having to memorize anything. So if you can clearly identify what the base is and what the exponent is, the exponent tells you how many times to use the base as a factor. So here in this example, you see 8 squared. That tells you to use 8 as a factor twice. But if we come over here and we look at these two, comparing the difference between them, this top one, we have a base of 2x, and then the exponent is cubed. That's telling us to use 2x as a factor 3 times. If we use 2x as a factor 3 times, that's the same thing as saying 2 cubed times x cubed, which is 8 cubed. And then if we look at this one here, be very careful with this one. The base is just x. This is technically the same thing as 4 times x to the 6th. So the exponent is applied directly with the base. If you don't see parentheses, it is only with the term it's directly related to. So that's telling you to use only x as a factor 6 times. If you remember the base and exponent rule, you don't necessarily need to memorize any of the other properties as far as the basic power, quotient, product, and so on. But two others that are extremely important, especially for this lesson, are negative exponents and zero exponents. So for negative exponents become positive in the opposite location. So if you have a negative exponent in the numerator, it becomes a positive exponent in the denominator. And if you had a negative exponent in the denominator, it becomes positive in the numerator. I'm going to give you the opposite example. If I had 1 over a to the power of negative n, this would be a to the power of n over 1, or just a to the power of n. So this here is the opposite of the one that I already typed for you. And the last important one to memorize is 0 as an exponent. This should be the easiest one to memorize because any number raised to the power of 0 is equal to 1. It could be 1 raised to the power of 0 and the answer is 1. It could be 250 million raised to the power of 0 and your answer is still 1. So anything raised to the power of 0 is equal to 1. If we go through these 4 on your own problems, just using our basic exponents, number 1, we have 2 to the power of 0. The answer to that is 1. Number 2 is 4 raised to the power of negative 2, which is the same thing as 1 over 4 squared, becomes positive in the denominator, which is 1 over 16. Number 3 is telling you to use the base of 6 3 times. So 6 times 6 times 6 is 216. And number 4 is telling you to use the base of 2x twice. So 2x times 2x, which is the same thing as 2 times 2, or 4, and x times x, which is x squared. All right, next we need to talk about some vocabulary. All of these vocabulary terms are terms we've already talked about this year. So let's quickly go through the formal definition of them. So starting with an asymptote, or what an asymptote is. Asymptotes are a line that a graph of a function approaches, it never touches or crosses. So the parent function of an exponential function, because that's what we're dealing with, always has an asymptote at y equals 0, and that's a horizontal asymptote. Of course, this can shift up or down with the function, but that's where the parent graph has an asymptote. When we're graphing, the y-intercept is another important factor, and this is where the graph crosses the y-axis. If you were doing this algebraically, you would set x equal to 0 and you would solve for y. For the parent function, the y-intercept is always at 1. Next, we're looking at the domain. Domain is input values, or x values, and the range is output values, or y values. But either way, if you're working with the domain and range, that means you are writing them in interval notation. Okay, exponential functions are generally in the form of a times b to the power of x. So while this is the general form, they can look much more complex, but either way, it's a number multiplied by a number or an expression multiplied by an expression, and the second expression being raised to some power. That is what an exponential function looks like. So if you have exponential growth is telling you that your a value is greater than 0 and your b value is greater than 1. Exponential growth is a representation of a quantity that increases slowly at first and then very rapidly after time goes on. The rate of change increases over time. Exponential decay is when your a value is greater than 0 and your b value is between 0 and 1. In this case, the quantity decreases very rapidly at first, and then it starts to slow down. In either case, either of these parent functions, because they're both parent functions here, the horizontal asymptote, abbreviated HA, is always going to be at y equals 0. So until that graph shifts up or down, that's where the horizontal asymptote is. Okay, graphing functions. So the first function is going to be an example of exponential growth. I know this because it's technically 1 multiplied by 2 raised to the power of x. So we're going to graph growth. And for exponential functions, the parent function changes depending on the value of b. So in this example, your b value is 2. So 2 to the power of x is your parent graph. Okay, this graph actually doesn't have any transformations, so that is all we'll be graphing is 2 to the power of x. So you should make a table of values to start with, but once you get used to doing these, you'll probably be able to do many of them in your head. We're going to test 5 values, starting with -2. -2 raised to the power of, 2 raised to the power of -2 is the same thing as 1 over 2 squared or 1 over 4. So your output is 1/4. If we test -1, we have 2 raised to the power of -1, which is the same thing as 1 over 2, 2 to the power of 1, which is just 1/2. So we'll stop there. If we test 0, our function is going to be 2 raised to the power of 0, but anything raised to the power of 0 is 1. If we test +1, 2 raised to the power of 1 is 2. And lastly, if we test 2, our function 2 squared is equal to 4. So these first two are negative exponents. You need to make sure you know your negative exponent rule for those. The third test point is the 0 value, which is always going to give you an output of 1. And then the last two inputs are just your values of 1 and 2, which should be easy enough to test. So when we graph this, we start by plotting a point at -2, 1/4, -1, 1/2, 0, 1, 1, 2, 2, 4. Remember that you're graphing along that asymptote, which is at y = 0. That would be this line here. So we're not going to indicate that that graph touches or crosses the x-axis. We're just going to indicate that it approaches it and continues up at a rapid rate. Okay, number 2. Our a value in number 2 is 1. Our b value is 1/2 raised to the power of x. So whatever term is raised to the power of x is going to be your parent graph. For number 2, our parent graph is 1/2 raised to the power of x. And if we test our 5 key values, we start with -2. If we had 1/2 raised to the power of -2, that is the same thing as saying 1 raised to the power of -2 divided by 2 raised to the power of -2. Because you have two negative exponents, you can switch the location and they become positive. 2 squared is now in the numerator, 1 squared is in the denominator. 2 squared over 1 squared is 4. Next we'll test -1. 1/2 raised to the power of -1 is the same thing as 1 to the power of -1 over 2 to the power of -1. Swap locations, this would be 2 over 1, which is just 2. Next is 0. Anything raised to the power of 0 is equal to 1. We have a value or an exponent of 1. 1/2 raised to the power of 1 is equal to 1/2. And lastly, 2. 1/2 raised to the power of 2 is 1 squared over 2 squared, which is 1/4. So once we plot all these points, we plot a point at -2, 4, -1, 2, 0, 1, 1, 1/2, 2, 1/4. Our horizontal asymptote is at y = 0. And if we were to indicate the domain and range on this function, you can tell that the graph extends in both directions on the left and the right, so your domain is negative to positive infinity. But for the range, this graph never goes below that horizontal asymptote. It also never touches or crosses that, so we cannot include it. That means it starts at 0 and heads up towards positive infinity, not including 0. And number 2 is an example of decay. So 1, we have growth. 2, we have decay. Both of them are the general form of a times b raised to the power of x. Now we're going to get into our transformations. So when you're graphing transformations of exponential functions, you must begin by graphing the parent function, as we always do. So here's your general form. I know it looks a little bit more complex than it did before. You still do have a times b raised to the power of x in there. So of course there's other stuff being added or subtracted to this, but you have your general form right there. Regardless of what other info you have in your function, b to the power of x is always going to be your parent function. That's it, nothing else, just b raised to the power of x. So if we slide down and we look at example 1, in example 1 we are asked to find the parent function. In this case, the parent function is b raised to the power of x. That's it. So here's your parent graph. It's y equals 2 raised to the power of x. Okay, we only have exponential growth if it fits the criteria of a is greater than 0 and b is greater than 1, which is the case here. So this is an example of exponential growth. And that's because the b value is greater than 1. Number 2, 4 times 1/3 raised to the power of x plus 2 minus 1. We have a lot of stuff going on here. B is 1/3. 1/3 raised to the power of x is your parent function. Okay, if we were asked if this is growth or decay, you have to make sure it meets the criteria. Is A greater than 0 right here? Yes, it is. And B right here is between 0 and 1. When B is between 0 and 1, that indicates that you will be graphing decay. You have all of these other transformations. So you have a transformation in this example that's a vertical stretch. You also have a shift to the left 2 units, and you have a shift down 1 unit. So we'll talk about those once we get to the graphing. For now, take a second and review your transformation rules. These are the same rules that we went over at the beginning of the year. All right, the horizontal shift is found by your value of h. If you have x minus h, you're shifting to the right. If you have x plus h, you're shifting to the left. The next transformation that you need to do, following this order, so first horizontal shift. Next, you need to look at your stretch, shrink, or reflection. That's found by either your A value, which is telling you that you are stretching or shrinking, and by your X value, which is telling you that the function is reflecting. You could also have a negative A value, which is a reflection as well. I should have mentioned that. So if you have a negative A value, it's reflecting over the x-axis. If you have a negative X value, it's reflecting over the y-axis. Those two notes are right here. Reflection over X, reflection over Y. So whatever variable is negative is telling you which way to reflect it. And lastly, you have your K shift. So the K shift, if you have plus K, you're shifting up. If you have minus K, you're shifting down. Make sure you follow the correct order. So horizontal, stretch, shrink, or reflection. Last, you're doing your vertical shift. Okay, number 1, we have to identify our parent graph. Your parent function is always the b value raised to the power of x. Here we have 2 times 2 raised to the power of x plus 1. Your parent graph is 2 raised to the power of x. We need to make our table of values, which actually we already made this table of values when we did the earlier graph, but let's go through that again. So our table of values is just for our parent function, and then we'll do the transformations. -2, if we have 2 raised to the power of -2, that's 1 over 4. Becomes a positive exponent in the denominator. 2 raised to the power of -1 is 1/2. 2 raised to the power of 0 is 1. 2 raised to the power of 1 is 2. And 2 raised to the power of 2 is 4. Plot these points. We have a point at -2, 1/4, -1, 1/2, 0, 0, 1, 2, 2, 4. This graph never touches or crosses the horizontal asymptote, and it rapidly increases. So that's our parent function. Now we have to do our transformations. So check to see if you have a left or right shift. That would be with your x value. We do not. Next, check for your A value or your reflection. This is a stretch vertically by a factor of 2. That tells us to multiply the y coordinates by 2. So if I come down to the graph, I'm going to look at all of my y coordinates, starting with this one right here. My y coordinate is 1/4. 1/4 times 2 is technically 2 over 1, which is 2 over 4, which simplifies to 1/2. So I'm going to replot the point of 1/4 at 1/2. This point right here has a value or a y value of 1/2. 1/2 times 2 is 2 over 2, which is equal to 1. Replot that point at 1. X values are not changing, only the y value changes. This next point has a y value of 1. 1 times 2 is 2. Here we have a y value of 2. 2 times 2 is 4. And lastly, we have a y value of 4. 4 times 2 is 8. Your horizontal asymptote still has not changed. It is still at 0. So this graph just looks like it's pulling away from the x-axis, or it's getting steeper faster than it was before. Okay, the absolute last transformation is your +1, which means you are shifting this graph up 1 unit. Shifting this graph up 1 unit requires us to take the pink graph and shift every point up 1 unit. When we do this, we also shift our asymptote up 1 unit. So our asymptote just went from y equals 0 to y equals 1. The horizontal asymptote has to shift with the graph, or else it wouldn't be a vertical shift. So here is the final exponential function, graphed in purple, highlighted in yellow right there. All right, we already identified our horizontal asymptote. It shifts with the graph. Next, let's identify the domain. The graph continues in both directions, so your domain is negative to positive infinity. The range, however, the range shifted up with the horizontal asymptote, so this graph never touches or crosses the line at 1, and it heads towards positive infinity. So your range is 1 with a round bracket to positive infinity. Number 2. For number 2, we have y equals -1 times 3 raised to the power of x plus 2, and then plus 1. So the first thing we need to identify is our parent function, which is just the b value raised to the power of x. So in this example, our parent graph is y equals 3 raised to the power of x. Before we do anything, we need to find the values for this function. So I'm going to test my key points, starting with a -2. 3 raised to the power of -2 is equal to 1 over 9. -1, 3 raised to the power of -1 is equal to 1 over 3. 0, 3 raised to the power of 0 is 1. 1, 3 raised to the power of 1 is 3. 2, 3 raised to the power of 2 is 9. So I can plot these points before I do my transformations. I have a point at -2, 1/9, -1, 1/3, 0, 1, 1, 3, 2, 9. Our horizontal asymptote is currently at y equals 0, so that graph is approaching the line at y equals 0, but never touching or crossing. Our first transformation is this value right there, so it's an A value of -1. So that would be a reflection across the x-axis. I know it's across the x-axis because of its location. If the negative sign was with the value of x, then it would be across the y-axis, but it is not. So this location indicates a reflection across the x-axis. And it's just a value of 1, so there's no stretch or shrinking. Oh, sorry. There's no stretch or shrinking there. It is just a reflection. We also have a transformation, and I'll label the order of these after. We also have a transformation right here of left 2. I know that I'm shifting left because that is with the exponent. That is our h value. And the last transformation is right here, which is +1, and that's telling us to go up 1. Okay, following the correct order, the first thing you should always do is your left or right shift. So I'll label that first. Then you do your reflection, stretch, or shrink. So we'll label this second. And lastly, always last comes your up or down shift. So that's going to be our third step. Okay, let's start with our left shift. So shift this left 2 units. Every point shifts left 2. We're reflecting across the x-axis. So just like we did before, you can multiply these points or you can physically just count. If this is 1 unit above, this is going to be 1 unit below the x-axis. This is 3 units above, so I'm plotting a point 3 units below the x-axis. This right here, this point's 9 units above, so my new point is going to be 9 units below. We reflected across that horizontal asymptote, so make sure it is clearly below this horizontal asymptote, which is currently at this location. All right, and our last step is to shift this graph up 1. So I take this pink line and I shift every point up 1 unit. Not only did the graph shift up 1 unit, but so did the horizontal asymptote. Is at y equals 1. It shifted up 1 unit. The domain is still all real numbers, negative to positive infinity. And now the range, this is the first time this looks a little different. The range of the green graph, I should erase some on here for you, it looks a little cluttered. So the range of this green graph is going to be from negative infinity to the line at 1. Make sure your most negative value comes first. Okay, and that green line, I'll highlight it in yellow, is your final graph. For the last part of the notes, we need to learn how to graph an exponential function using the number e. And the number e is a mathematical constant that approximates about 2.71, I think it's 718, something like that. Anyways, it's not something you have to memorize. That is the constant value. It's defined as the number that the expression 1 plus 1 over n to the power of n approaches. But either way, you guys don't have to memorize any of that. What you do have to know is where it is in your calculator. So if you have a scientific calculator or a graphing calculator, some sort of calculator such as this TI-84 Plus, E is when you push the second key on this specific calculator. It's when you push the second key and then this LN key, which is next to 4, and you see that it drops in this little value of e raised to the power of x, which you can insert your exponent for. If you use something such as Desmos Scientific, like this calculator here, the number e is when you hit function. I'll screenshot this. Okay, so on this calculator, and I'm going to delete this, but the number e is found right here. So you have to select function, and then right there where I highlighted e raised to the power of x. So that's where it is on desmos.com/scientific. So either way, or whatever calculator you have, there's multiple different ways to insert the number e. If you have a question or need help on it, I can help you out. Just let me know. So for this one, I already typed in my value. So for example, the first one of -2, I just used my graphing calculator and I typed in, I didn't even type in y equals, I just typed in e. I selected e, and then with an exponent of -2, I hit enter and I get 0.135. E to the power of -1 is 0.368. Any number to the power of 0 is 1. E to the power of 1 is 2.718. E to the power of 2 is 7.389. So once I have those values, I can graph them on my graph. And it's just a exponential function. It looks just like the others that we've done. Just make sure you have the correct values. In this case, the horizontal asymptote is still at 0. Your domain is still all real numbers. In this case, your range is from 0 to positive infinity. So the only thing that's different about this is that you use your calculator to find the value using e or the number e. So if you want to take a minute and do the two on your own, all the transformations are the same. You just have to have that parent function down. So definitely a good idea to make sure you memorize, I guess not even memorize, but make sure it's a good idea to make sure you know where this is in your notes.